Hello. Yeah. So good afternoon to everyone, and we are going to have the first tutorial on this GAN course, and I am going to do a very easy job of just discussing some very basic things related to this convex optimization. So today we are going to discuss about convex sets. So okay, so we just start from the very basic thing. Suppose this is the space, and we have 2 points here, x and y, and as we know that this x1, x2, and xn, and y is defined as y1, y2, yn, and we can join these 2 points in a space by a line segment. So how we represent this? So this line segment is represented by x, comma y, and this is the set of all z such that z can be written as lambda x plus 1 minus lambda y, where this lambda belongs to 0, 1. So this is the line segment joining any 2 points on space, and we call this as convex combination of these 2 points x and y. So convex combination of x and y. So if in place of this lambda we replace this lambda from any real number, then we have this affine combination. Affine combination of x and y, so it will be like, so we can write alpha x plus beta y, and this alpha and beta belongs to R. So in that case, we will have a line passing from x and y. So we can extend that. Otherwise, we have this convex combination. For what? Yeah, alpha plus, yes, along with this, alpha plus beta equal to 1. Because here lambda plus 1 minus lambda is 1, so along with that we have this alpha plus beta equal to 1. So for a convex set, this convex combination, so we can start from a point, and then we have 2 points, we can add them A and B. Suppose we have 3 points, and we can add like this, and this is a triangle. And then we have, so we can increase the number of sides in a polygon, and we keep on increasing like this, and if we keep on increasing like this, maybe when n tends to infinity, we will get a circle like this. So these are few sets, and what we can do that if you take any 2 points inside this set, and we join these 2 points, the line segment joining any 2 points is inside this set. In any set, if you take any 2 points in the set, maybe from here and here, anywhere. And then what we can do, we can have some other types of sets. Suppose we have some donut like this, and we try to find out any 2 points, and we join them. So this line segment goes outside of this set. We can have some other sets like this star, and again we have some points here, and this is outside this set. But there may be some other points, maybe in between, from where we can draw line segments throughout the set. So there are different types of sets that may be a feasible set of an optimization problem that we can deal with. So if we observe, formally we can observe that in these sets, the line segment is completely inside the set. But there are sets where the line segment is not for every point, because there are points where the line segment is completely inside the set, but there are points where the line segments are not completely inside the set. So if we define a convex set, so convex set, so what is the formal definition? So a set is said to be convex, C subset of Rn is said to be convex. This is convex. So if and only if this lambda x plus 1 minus lambda y belongs to C for every lambda in 0 and 1 and for every x and y in this set C. So this is the definition of the convex set. In terms of convex combination, we can say if a set is closed under convex combination then of its elements, then we call the set is a convex set. But what about this set? So here this convexity is not followed completely, but partially. So we call this set as a star shaped. So if you have a set, suppose S is a subset of Rn and it is star shaped, so there will exist one so star shaped at a point. Suppose at x bar in this set S, there is a point in this set. So this is the point x bar. So we can write that if and only if this x bar plus lambda y minus x bar belongs to that set S for every lambda in 0, 1 and for every y in that set S. So here this convexity is not followed completely, but at certain points we may have certain points in the set where this partially this convexity is satisfied. And for these sets, we may not have some points where, because if we have this point, we can draw, maybe there are few points in this space, but if we go outside, there are line segments which are outside this set. So along with this, we can have also a strictly convex set. We can have also this concept of a strictly convex set. So for example, if we consider this circular disk, so what will happen that if we take any point, any 2 points in this set, the convex combination is inside this set, that is in the interior of this set, right? So we can write that this lambda x plus 1 minus lambda y belongs to interior of this set C for every lambda in between 0 and 1. So if we take any 2 points in that set, so the convex combination excluding that point, because if we exclude 0 and 1, then we have this x and we have this y. So if it is 0, lambda is 0, then we have y. If lambda is 1, we have x. So all the other points are in between. So all the other points will be inside that set, will be in the interior of this set. So we have this concept of a strictly convex set. So first it should be convex, and then we have this concept of strictly convex set, which is not in the case of the sets where we have edges. Because if we take any point here, then and any other point here, x and y, then they are convex combinations, so it is not in the interior of this set. So this set is not, it is convex, but it is not strictly convex. So strictly convex sets are, you may consider that the is in the is a subset of the convex sets. So along with this convex sets, let us discuss some non-convex sets. Suppose we have this set defined like x1 and x2, and we can write this that x1 greater than equal to 0, x2 greater than equal to 0, and x1, x2 is equal to 0. So you can try to find out the feasible reason graphically, and then we will discuss. This is another set x1, x2, and x1 and x2 is equal to 0, and suppose we have this set x1 and x2, and we can write x1 greater than equal to 0, x1, x2 is less than equal to 0, right? So these are three sets, and you may try to find out the feasible reason of these sets. So this omega 1, if it is x1 is greater than equal to 0, so this is x1, and x2, so this is the greater than equal to 0, x2 is greater than equal to 0, and then we have x1, x2 is equal to 0. So we have this these two lines only, right? Is it correct? So you can see that omega 1 is not a convex set, but we can observe that at the origin it is a set which is star shaped. So it is a non-convex feasible reason, but it is a star shaped at the origin. Now what about omega? So this is omega 1. What about omega 2? So here we have x1, x2 equal to 0. So either x1 is equal to 0 or x2 is equal to 0. So we have x1, x2. So we have this reason. So we have this feasible reason, and you can again observe that this feasible reason is also not a convex feasible reason, but at the origin it is a star shaped. Okay. And what about the third one? For the third one, we can see that this x1 is greater than equal to 0. So we have to break this in two parts. This if when x1 is greater than 0, what will happen? This x2 will be less than equal to 0, and x2 is less than equal to 0. And when x1 is equal to 0, there is no constant on x2. So when x1 is equal to 0, then x2 can take any value in R. So x1 is, so what will be the feasible reason? So this x1 is greater than 0 and x2 is less than equal to 0. So we are going on the, this will be the space for the first one. And what about this? X1 is, so it can take all of this x2. So this line. So again you can see that this set is also not convex, and but at the origin it is star shaped. And if you are working in non-convex optimization, you may be able to recognize these sets. So this is actually a feasible reason of a mathematical program with equilibrium constants. Equilibrium constant. What about this? So this is feasible reason of mathematical programs with switching constants. Switching constants, and this is a feasible reason for mathematical programs with vanishing constants. So in optimization problems, we may have convex feasible reasons that we will see later, that we are looking at different optimization problems that we have discussed, like linear programming problems and convex optimization problems. And if we move from convex to non-convex optimization problems, we may have feasible reasons which are. So you can find out plenty of literature on equilibrium and problems and switching problems and vanishing problems. So, but one thing we can observe that these sets are also star shaped at certain points. So based on the property of the feasible reason, we have to deal with the optimization problem. So now coming back to this convex sets, because it is of interest, so we can have different examples of convex sets that we were looking. So the first thing, that the empty set, this is a convex set. Then we can have singleton set, which is convex, and we can have all the space Rn. It is a convex set. Then we can have this Euclidean ball, or any ball of center Z and radius R. So that was discussed. So suppose it is in Rn, and then x minus z is less than equal to R. So this is a closed ball with center Z and radius R. But then we, depending upon the norm of this, we can have different shapes. So suppose we want to have a P norm, and suppose Z is the origin. So for different P norms, so for a standard P norm, suppose we have this P norm. So it will be like P x1 and to the power P plus x2 to the power P, and then we go x n to the power P, right? So for different values of P, we have different shapes of this structure. So suppose this P is, so let me, so for the P equal to 2, it is the standard Euclidean norm, right? And if we have this P, suppose it is 1, then what will happen? We can have this norm for P equal to 1. The shape will be like this. But for P 1 by 2, it will be like this. So you can see that, so this is for P equal to 1 by 2. So this is for P equal to 1, and this is for P equal to 2. And we can increase this value of P, and if we keep on increasing, we will have this type of ball. So why? So you can observe that for P equal to 1 and above, it is a convex set. But when P is less than 1, it is a non-convex set. So we have P equal to 1 by 2, it is not a convex set. It depends on the choice of this P for a P norm, right? Now we were talking about this half spaces. So, or suppose we have this set, and this set is defined as x in Rn, such that V R, sorry, V x is less than equal to V is any element in Rn and V is not equal to 0. So this is actually the half space, okay? So we were talking about this half spaces, and this half space is also a convex set. And then this, if in place of this inequality we have equality, we have affine plane. So we have this affine plane. So it will be defined like x in Rn, and V x is equal to R, right? So of course V is in Rn and V is not equal to 0, right? And then we have seen this, these are regular polygons, these are also convex sets. And earlier today we were discussing about linear programming problems. There was a presentation by Professor Mishra. So the feasible reason of a linear programming problem is also a convex set. So we know that, and so linear programming problems can also be treated as a special case of convex optimization problems, because a linear function is both convex and concave. So the set of all, the set of all feasible points of a linear programming problem is a convex set. So you can have this feasible set like this, and x in Rn, such that you have Ax, this is less than equal to b, and x is greater than equal to 0. And you can use the definition of this convex sets directly, and we can apply here to find out that this feasible reason of a convex optimization problem is also a convex set. Linear programming problem is also a convex set. And along with this inequality, if we have this affine space, suppose we have Bx is some C like this, then again it will be a convex set, because then it can be written as intersection of two sets, one which is with inequality, that is half spaces, the other one will be affine plane, and then we can write that intersection of two convex sets is also a convex set, right? And we can extend this for any number of sets which are convex. So if you have a finite number of sets, Ci and I is in I, so we have seen is convex if this Ci is convex for every I in I, right? So we can have intersection of convex sets which are convex. So these are the properties that preserve the convexity. But what about the union of convex sets? Suppose we have two sets like this omega. So we have seen this omega 1, omega 2 union of convex sets. So suppose we have a set omega 4 which is given by x1 comma 0. Of course x1 is in R, x1 is in R, and we have another set omega 5 which is 0 comma x2. X2 is in R, right? So what about these two sets? Are these convex? So this is the x-axis and this one is the y-axis. So if you take union of both these sets, you will have this set omega 1. No, omega 2, right? So you will have this set omega 2. But we can see that this set omega 2 is not a convex set. So it means that these two sets whose union is not a convex set. But we will see that we can take the convex hull of the union and then the convex hull will be a convex set. What about convex optimization problems? So in general, because we have seen linear programming problems and which are special cases of convex optimization problems, so what is the structure of a convex optimization problem? So the function will be a convex function. So the function will be a convex function, and then so we have to minimize f of x subject to x belongs to C, where this f from maybe from Rn to R is a convex function. So you know the definition of convex function. Maybe in some tutorial we can discuss more about convex functions and its properties. And this C is a subset of Rn is a convex set. Is a convex set. So this is the basic structure of a convex optimization problem. And for this convex optimization problem, what will be the structure of this C? So when this set will be a convex, so suppose this C is defined like x in Rn such that we have this GIX less than equal to 0, where I is some finite index set. So if this GI, and these are from Rn to R, are convex functions. Convex functions. Then this set C will be a convex set. Then this set C will be a convex set. So, and we can try to prove this result, because how to, so this is one structure of this convex optimization problem. Like if we have this C, it can be of any structure in any way. We can, I mean, if we have this inequalities or constraints are not convex, one special case is the linear inequalities. So if we write as GIX, so one special case will be linear inequalities. Linear inequalities. So this GIX we can write like A1x plus A1x1, A2x2 and AN xn minus BI, suppose BI. Or we can have this indexing AI1, AI2 and AIN xn minus BI. So this is one structure of this GI. So if these functions are linear, then also it will be a convex set. That we have seen for a feasible reason of a linear programming problem. Now what about uh, general convex functions? So if we have GIX, so we have to show that this set is a convex set. Hmm. Which one? This one. This is C, and which one you were talking about? That is the definition of a convex set. That is the definition of a this C is different from that. That is a general convex set. Any set C. If you have 2 points and you try to join those 2 points and the line segment is completely inside that set, then we call that set to be convex. Okay. Now we are going to show that if this set C is represented by this inequalities. Suppose we have this linear programming problem and we have these lines, right? These are different lines. So this is, suppose this is line 1, line 2, line 3. These are inequalities like this. AI1. So in place of I, you can 1, 2, 3. So, and this is the feasible reason, right? This is the feasible reason. So now we have to check whether this feasible reason is a convex set or not, right? So how to check? So one is by definition, direct definition, that this, you take any 2 points in that set and then the line segment must be inside that set. The other way is to use that the intersection of the convex sets is also convex. So you can see that this is intersection of half spaces. Okay. So what are the half spaces? This is one half space, this is another half space, this is another half space, and this x1, x2. Okay. So there are 1, 2, 3, 4, 5. 5 half spaces are there. So it is intersection of this 5. So every half space is also a convex set. So this is intersection of half spaces. So therefore it is also a convex set. So either we are going to use directly the definition or we are going to use some properties of convex functions, convex sets, by which we can detect whether the set is convex or not. So now in place of linear, we can replace it by some non-linear functions, right? So how we can replace? So the structure of the feasible reason is like this. Okay, this is the structure of the feasible reason. Now what we can do, and we know that we were discussing in the previous class that these are the corner points. Okay, so what do you mean by a corner point of a set? Corner point of a set. So a point which cannot be written as a convex combination of 2 distinct points of the set, right? So suppose you take this point. So can you find, so these are A, B, C, D, E, different points. So can you find out 2 distinct points of the set whose convex combination of will be this point C? Suppose you take 1 point here. So for being a convex combination, it must be on a straight line segment joining. But this point is going outside of the set. For if you approach from this side, what will happen? You have to go outside the set, right? If you approach from, so anywhere these points, you cannot find two distinct points which can be written as a, which will represent this point as a convex combination, right? So that is why these are corner points. And in linear programming problem, the result is that if it is an if it is an unique optimal solution, if the LPP, if the linear programming problem has an unique optimal solution, then it will be a corner point feasible solution, right? This is the result. Very, very simple, because if you have this corner point feasible solution, then what you can do, you cannot, so what is the negation of this result? If it is not a corner point feasible solution, then it will not be an unique optimal solution of the linear programming problem, right? So that is why we are trying to find out corner points of this set. Now, so for a convex optimization problem of this type, what we can replace, so for in place of linear functions, we can replace by non-linear function like this, right? We can have non-linear functions. So suppose this is one non-linear, this is another, this is another. So these are non-linear functions. So what we can have, so you see this is the feasible region, right? So when we have non-linear functions, it can be represented by any function like gix, right? And suppose this gix are some convex functions, right? So we can have gix, suppose g1x, x square, and g2x, anything e to the power x, and we can have g3x, some linear function, suppose x, right? So we have the intersection of convex functions now. So in place of linear functions, we have convex functions. So the point is that whether, if you have this convex functions, whether this set will be a convex set or not. So how we can prove that? We can directly use the definition, right? So if we use the definition, so what we have to show? That this set C is a convex set. To show C is a convex set, right? We have to show that this set C is a convex set. So how we can show that? So we have to take 2 points. That is, you take any 2 points x and y in C and lambda in 0, 1, then lambda x plus 1 minus lambda y must be in C. Okay, that is, this inequality must be satisfied. So we start from this gi lambda x plus 1 minus lambda y, right? But now this gi is a convex function. So when this gi is a convex function, we can write this is less than equal to lambda gix plus 1 minus lambda giy, right? By convexity of gi. So by convexity of gi, we can write this. Now what is gix? Now this gix is less than equal to 0. So, and this lambda is in between 0 and 1. So we can write this value is less than equal to 0 and this value is also less than equal to 0. Okay. So in total we can write this is less than equal to 0. So value of the function gi at any convex combination of 2 points is also less than equal to 0. It means that this lambda x plus 1 minus lambda y also belongs to this set C, right? So this is one structure of the feasible region. It may have many structures, like we have seen that it may have a non-convex structure for equilibrium problems, for switching problems, for vanishing problems. It may have a non-convex structure. But for this structure, if we can write the feasible region as these inequalities which are represented by convex functions, then this set will be a convex set, right? It is also possible that we can write these inequalities like we may have non-convex inequalities or non-convex functions, but their intersection is a convex function. Okay, you may try to find out a feasible region whose the constants are not convex, but their intersection, and or maybe you can replace this convex functions by quasi-convex functions and then try to find out whether you are able to get a convex set or not. For example, if we have a quasi-convex function, the lower level set will always be convex. So that is another example of a convex set. So for if a function is a quasi-convex, if f is quasi-convex, then the lower level set of f with respect to alpha is a convex set. Okay. So we can have different structures of the optimization problems where we are able to find out these convex sets. Also for convex, so we have discussed this, but this is AP graph of a convex function is also a convex set. Is also a convex set, right? So we have seen that if we have this set and then we can find out this. So one way to detect the whether the function is convex is to find out the epigraph of the function, and then we can check whether the epigraph is a convex set or not, right? So by using convex sets, we can determine whether a function is convex or not. So we have seen these few operations that preserve convexity, and so intersection of two convex sets is also a convex set. And then but union is not, but then you can have this Cartesian product of two convex sets. So if omega 1 and omega 2 are convex, then this Cartesian product, which is defined as suppose x1 and x2, such that this x1 is in omega 1 and x2 is in omega 2, is a convex set, right? And you can directly use the definition of the convex sets to find out. You don't need any property. So there are certain operations under which this convexity is preserved. Operations that preserve convexity. So the first one you can write this translation. So what is translation? You have any set C and you can add. By C we mean a convex set. So you have a set C and you add any number to this. So you have this, this will be X plus B, such that this X belongs to C. So you have a set and every element of the set is added with some number, and that will be uh, a new set. But this will preserve the convexity, and you can use the definition directly to find out whether this is true or not. Then we have scaling. So you multiply with any number, so alpha x such that x belongs to C. So this is scaling also, it preserves the convexity. If the set C is convex, then alpha of C will also be convex, right? Now this one, the convexity of a set is preserved under affine mapping, right? So what is affine mapping? So suppose you have a function b from Rn to Rm. What we do, a type of affine mapping in linear programming problems also, because we change the dimension of the feasible region when we introduce slack variables or surplus variables. So we change the dimension of the feasible region. But so what we are doing, we are actually, so suppose we are in Rn, and by using slack and surplus variables, we are changing the dimension of the feasible region. So from Rn to going to Rm. So this is a type of transformation. So when this transformation will be affine, so if we can write like Bx is defined as Ax plus B. Okay. So this A is any matrix and B is, so this affine mapping, you know, maybe from linear programming problems. So you you have this A, so it can be defined as a matrix Aij m by n, and X is also, X is of course this x1, x2 and xn in Rn, and then when you multiply, this will be m by n and n by 1. Okay, so this B will be this B1, B2, and it will go to Bm. So this will be in Rm, right? So this mapping is said to be affine, and when you put this mapping like this, this is X, and you apply B on this set C. So if C is convex, then you apply this affine mapping on C is also convex, right? And you can try to prove this maybe by using the definition, right? How? So B of, so what we have to do? So to prove that B of C is a convex set, we need to show that if you have two elements in B of C, then their convex combination will also be an element in B of C. But if you have two elements in B of C, then what will happen? You can write it as like this. Any element, so we can write it like this, right? So, I mean, if there exist, if P and Q belongs to B of C, then there exists this X and Y in this set. This one is C. In C such that, so what you can write, this P can be written as AX plus B, and this Q can be written as AX, AY plus B, right? And now what you have to do, you have to show that if you take the convex combination of P and Q, that will also be an affine mapping, right? So now if you have lambda P plus 1 minus lambda Q, so now in place of P we can write A X plus B, and in place of Q we can write A Y plus B, right? And then we can distribute this lambda because this is a scalar and it can go inside. So what we can write A lambda X plus, this one will also be added, 1 minus lambda Y, and then what about this B? So it will be lambda B, and here it will be 1 minus lambda B, so it will be cancelled out, we have only B, right? But what is this? This is convex combination of X and Y, and X and Y belongs to C, and C is a convex set, so this belongs to C, right? So so what is this? This is an affine mapping, right? So A, an element of C plus B. So what? So it tells that this must belongs to B of C, right? Because this is an affine mapping. So this belongs to B of C. So the point is that we may have different structures of the feasible reason or the functions, but then we have to locate that how we are trying to find out the convexity. So here, by using affine mapping, we are trying to find out the convexity, right? Similarly, if you add two convex sets, you have also this convexity, and so maybe we stop here, and then in the next tutorial we can discuss more about convex sets, convex functions, separation theorems, and we'll try to find out, because KKT condition is not discussed, so we will trying to find out that how we are getting this KKT condition. Okay? If you have any question you can ask. Right? One good exercise will be you try to find out some A and B, and you take a convex set. Okay, you take any convex set, omega defined as x1, x2, such that x1 square plus x2 square less than equal to 1, right? So this is omega, and then you try to find out A. You take any 2, 0, 1, 3, and you take B. You take anything like 1, 2, 3 maybe, right? And you try to impose this. So you have this shape, just to visualize that what is happening. So you have this circular disc, and you try to impose this transformation on this circular disc and see what happens, what you will get. Okay, what will be the shape with this, and you try to find out different A and B and how this shape will be changed. Okay, so that will be a good exercise. Okay, then if you have no queries, then we can end the session now. Thank you, and tomorrow we will meet again at 10 a.m. in the morning. Yeah.